Good morning and welcome to Litmus Test. Last time when we left off we looked at three-dimensional crystals and I left you with the question, what lattice does table salt sodium chloride have? If you got body-centered cubic, good job. Today we're looking at something a little different. We're looking at defects, imperfections in crystals. Nobody's perfect, and that includes crystals, which are among some of the more perfect things we do have in this world. So to look at defects, first today we're just going to look at what types of defects exist. Sometime in the future when we get into thermodynamics, we'll talk about why they will always exist. But we'll start simple, and we're going to start with these things, the point defects. Point defects, vacancy on the left, substitution on the right, and more complicated ones to come, are just simply when an atom is in the wrong place. In a vacancy on the left, an atom is simply missing. I've used glass to represent the void. It's just not there. And in substitution on the right, there is an atom where a different atom is supposed to be. A white atom should be in the middle of that cross, and instead there's a black atom. So there's an extra atom in place. Now, a lot of these crystals that we talk about are really ionic crystals. So instead of atoms, we're really talking about ions, which is just atoms, but they have an electric charge on them. Electric charge comes in two flavors, positive and negative, which is perfect, because over here we have a Schottky defect. A Schottky defect is a vacancy in a pair of ions. So you'll notice that both a white and a black ion are missing, which is like saying a positive and negative ion are missing. With this of regular vacancy or regular substitution, we might alter the total ionic charge of a crystal, but in a Schottky defect, the total ionic charge stays the same. And so when we look at ions, we see this type of defect happening much more frequently than just a regular vacancy or just regular substitution. Those are defects that we see very frequently in metals and alloys, other non-ionic compounds. We also have this Frenkel defect. In a Frenkel defect, an ion moves to an open space. In chemistry and in crystals, we call open spaces interstitial spaces. Interstitial, inter meaning between, and stitial meaning stuff. So the space between stuff. So the interstice is just a space between two things, and in this case it's two atoms or two ions. Notice that the white atom was supposed to be where the glass is and is moved to this other location. So it is taken up resident in an interstitial space. That's a Frenkel defect. It's just an ion moving to an open space. That's a slightly different. It's a little bit like the substitution, a little bit like the vacancy. Finally, we can also have impurities. Impurities come in two types, substitutional and interstitial. If you needed to know how to spell that word, here it is. A substitutional impurity is when we just have a plain out different atom that's not even supposed to be in the crystal there. So it takes the place of a regular atom. In this case, we see that the black atom was supposed to be here, and now instead it's Lattice. On the right, we have an interstitial impurity, where an impurity is simply sitting in a space where like the atoms around it are fine, it's just in an open space. It just happened to fit in there. Now, in a regular crystal, often other atoms or other ions, these impurities, are going to be a different size than the regular atoms, and so these lattices will end up being distorted, either squished out of the way or sort of crushed in. That's hard to represent with Minecraft. You'll just kind of have to imagine that these black atoms would be distorted by a couple of, like maybe half a block out of place in one direction or another. Compared to the other types of point defects, impurity defects are a little more rare. Because of that, you can use the technique called recrystallization to purify some of your material. That just means if there are a small amount of impurities in a large solution that mostly contains one substance, let's say you have a lot of sugar and a little bit of salt. You can recrystallize the sugar and most of the salt will be excluded. You can then pull the sugar crystals out, redissolve them, and recrystallize them again to purify them even more, removing more of the salt. And this happens because when the salt is in the way of the sugar, it pushes on all of the sugar atoms, causing them to stretch or shrink or just distorting the lattice. To see an example of what we mean by distorting the lattice, let's fly over here and ignore these two spaces to take a look at this space here. This space illustrates a distorted lattice. I've used some redstone here and powered it so you can see it a little more clearly. And this redstone just kind of shows lines of atoms that are in a row, and these are called line defects. Notice at the top that there are 5 lines of atoms, and at the bottom there are only 4 lines of atoms. If you extended this into the 3 dimensions by stacking more of these copies on top of each other and below each other, you would end up having a plane right here that is supposed to be filled with atoms and is not. This type of defect is again a line defect, and it is considered a one-dimensional defect, whereas points are zero-dimensional defects. That's just because points are sort of zero-dimensional, kinda, and lines are kinda sort of one-dimensional. And you'll notice that this is like a line, because if this were running straight through, up and down, there would be a line right here where it's missing. Alternatively, you can look at it as, well, this line is distorted, this line just stops, this line is distorted, and so on. Notice that in this type of distortion, the crystal spacing, the lattice spacing, tries to stay constant. So when this line ends, these atoms actually move inward to try and fill this void. And in a bigger crystal, they will. Finally, we look at another type of defect called the grain boundary. I've outlined grain boundaries here in redstone, but you should be able to see it if you don't have the redstone in this case. Even if you have trouble seeing it here, you can search Google for grain boundary and you'll see a lot of really good pictures. In this case, this one is really simple to illustrate. We just have a repeating pattern of white and black, and along the grain boundary we've just swapped which squares are white and which squares are black. Notice that above and below the grain boundary there are regular normal crystals, and the crystal hasn't changed. We don't say that the lattice is any different. We don't use a different word to describe what the lattice is. The parameters haven't changed. This is just essentially 2 different crystals that grew next to each other and intersected. That's mostly what a grain boundary is. Not always. The line defects that we saw before, as well as another 3-dimensional version called a screw defect, these can also create grain boundaries, but very frequently, particularly in metals or anything else that is cooling down, grain boundaries are just something that happens when one crystal is growing into another crystal and it just runs into each other. In this particular case, you'll notice that the crystals don't have any direction, but if we fly over here, now all of a sudden the crystals have a direction to them. You'll notice that I've built this alternating rows of 4 and 4, and here you'll see that we have a vertical, horizontal, and diagonal sets of grains. And there's another vertical one down in the corner hidden by my clock. Let's get rid of the clock for the moment. Nope. Still have that there. And so we've got this vertical, diagonal, and horizontal grains with this grain boundary in between. So you can see that grains and grain boundaries are going to be very complex things in a large run. In a large material, these grains and grain boundaries appear all over the place, and they're a major source of mechanical defects and mechanical failures. They're a major source of stress and strain because these places are weak places. These are where grains could run into each other and fall apart because the bonding between 2 grains might not be as strong as the bonding within a grain. So if we want to remove these, particularly things like this, we can do a process called work hardening, where we bend and bend and bend, or hammer and hammer metal or other material to slowly work and iron out these grain boundaries and iron out these line and screw dislocations. Mostly what happens is this vacant line here ends up moving over and over again until it sort of disappears and all of the lines here realign themselves. Hard to show in Minecraft. You'll have to imagine it or look it up. On the other hand, if we want to add some of these defects, we can just heat up our material or melt and recrystallize it. And that will add a lot of these grain boundaries, line defects, and other sorts of things. Adding impurities and defects sounds really weird, but adding impurities can actually make a material very, very hard, like carbon going into iron to make steel. And sometimes we want our materials to be more defective just so that they're a little bit more flexible. Plastics in particular might be a little bit, might have a lot of these like grain boundaries. The plastics might have a lot of these little defects in them, and that's what makes them very flexible. On the other hand, there are some times when we want a material to be hard and brittle, and then we want to work out all of these various impurities and defects and so on. So that's been defects. There are other types of crystal defects for three-dimensional crystals, but because they're hard to draw and visualize, I'm not going to draw them here. I'll let you go to Google and look them up yourself. This is really an introduction video anyways, so hopefully you leave today with a slightly better understanding that crystals aren't perfect, and this is what some of the imperfections look like, with these point, line, and grain defects. So until next time, stay safe and don't catch on fire.